This lesson will be an introduction to functions. A function is a rule that assigns each input exactly one output. We'll call the output the image of the input. The set of all inputs for a function is called the domain. We already know this from our algebra class. But we're going to introduce a new terminology here. The set of all allowable outputs is called the codomain. And we'll discuss in just a minute how that's related to what our familiar concept is, the range. They're not exactly the same. But first, let's look at this notation. We would use this notation, f from x to y, to describe a function that is named f with domain x and codomain y. So you'll read this f is a function from x to y. But this doesn't tell us which function f is. In order to know which function f is, we should define or describe a rule. Often, this will be done by giving a formula. Like in our algebra class, we would have a formula like f of x equals x squared. But that's not the only way to describe or define a function. So for example, let's consider the function f from the set of natural numbers to the set of natural numbers, defined by f of x is equal to x squared plus 3. We want to note that the domain here is the set of natural numbers only, whereas in your algebra class you probably would have taken the domain to be the set of real numbers. But since this is a discrete mathematics class, we'll focus on objects like the natural numbers. You'll also notice here that the domain and the codomain are the same set. So the rule of the function is to take an input, an element from the set of natural numbers, multiply it by itself, and then add 3. This rule works because we can apply this to every natural number, and the result will always be a natural number. So for every element of the domain, the rule will work, and for every element of the domain, we'll get an element in the codomain. So this is a valid function. But notice that not every natural number is actually going to be an output of the function. The rule is x squared plus 3, so there's no way to get 0 from x squared plus 3, or 1, or 2, or 5, etc. The set of natural numbers that are actually outputs are called the range. So in this case, the range is going to be 3. If I plug in x equals 0, because we include 0 in the set of natural numbers, I get 3. If I plug in x equals to 1, I get 4. If I plug in x equals 2, I get 7, and so on. So the range is all of the natural numbers that are 3 more than a perfect square. The key thing to making sure that a rule actually defines a function is that there is exactly one output for each input. The description of the rule can vary greatly. Like I said, we'll often write a rule like x squared plus 3, but you could also just list the images for each input, or describe the function with a table or a graph. So here are some examples. F from the set of integers to the set of integers defined by f of n is equal to 3n. So n is an integer, and our function multiplies it by 3. Then the domain and the codomain are both the set of integers, because that's how it's written here. However, the range is only those integers that are multiples of 3. The range is just going to be 0, 3, 6, 9, 12, etc. Another example would be something with a smaller domain, like g is a function from the set 1, 2, 3 to the set a, b, c. And the definition we'll give is just g of 1 is c, g of 2 is a, and g of 3 is a. This is a perfectly valid way to describe a function. The domain here is the set 1, 2, 3. The codomain is the set a, b, c, but the range is only a and c because none of 1, 2, or 3 got sent to b. So note then that g of 2 and g of 3, since they both go to A are the same element in the codomain, and that's okay, as long as each element in the domain only gets associated to one element in the codomain. Another example is H from the set 1, 2, 3 to the set 1, 2, 3, and we could describe the rule of the function pictorially. Here you'll see that these arrows indicate that the element 1 in the domain goes to the element 2 in the codomain. The element 2 in the domain goes to the element 1 in the codomain. And the element 3 in the domain goes to the element 3 in the codomain. So this kind of representation can be helpful in visualizing the function. In this class, we'll often be working with functions with finite domains, so this kind of a picture might be more useful than a traditional kind of graph. Just so that you can see, a graph of such a function would look like this picture here. Since there are only 3 elements in the domain, we just represent the graph by these 3 dots, and we do not connect the dots. It's very important to realize here that this is the graph. We're not going to connect the dots or draw in any type of curve, because if we had a curve, that would imply that the domain were an interval of real numbers and hence would no longer be discrete. Another way of describing a function would be a table, as is seen here. So I could read it from left to right. The inputs are 0, 1, 2, 3, and 4. With the input 0, I'm associating the element 3 from the codomain. With the element 1 from the domain, I'm associating 3 from the codomain, and so on. Or we could further simplify this table by just getting rid of this column and writing it as a matrix. So again, I have 0, 1, 2, 3, and 4, and the second row tells me which element in the codomain I'm associating with each element in the domain. But we want to make a note here that we use this notation that looks like it's a matrix, but we are not thinking of this in the same way that we thought of matrices if we took linear algebra. It doesn't make sense to do matrix operations here or row reductions or anything like that. It is important to know how to determine if a rule is or is not a function. Sometimes drawing these diagrams can help. So for example, we have a question here: which of the following diagrams represent a function? Let's take X to be the set 1, 2, 3, 4 and Y to be the set A, B, C, D. So you can see here your domain is across the top, 1, 2, 3, 4. Your codomain is across the bottom, A, B, C, D. And we need to determine which is a valid function and which isn't. We know that in order to be a function, for each element in the domain, I can associate exactly one element in the codomain. So if I look at the first example, I see that 1 is associated with D in the codomain, 2 is associated with A in the codomain, 3 is associated with C, and 4 is associated with B. That's a perfectly valid function. G is also a perfectly valid function. In this case, I have 2 elements going to A, and I don't have anything going to C in the codomain, but that's fine. There's nothing that says that every element in the codomain has to get hit. But if we look at H, there are a couple of things wrong with H. So first of all, I didn't associate any element in the codomain to the element 1. So that is a problem. It's okay if it happens in the codomain. It's not okay if it happens in the domain. So I have to send 1 somewhere in order to be a function. The other problem that I have is that the element 2, it got sent to 2 different elements in the codomain. And that's also not okay. We can only have a unique element in the codomain to associate for each element in the domain. So we could use our 2-line notation to describe these pictures above. For F and for G, you'll see 1 associates with D, 2 associates with A, 3 associates with C, and 4 associates with B. That's exactly what's going on in the first picture F, and similarly G. But if we tried to do the same thing for H, it wouldn't make a whole lot of sense. You'd have 1 isn't going to any element in the codomain, and 2 is going to both A and C. So I couldn't write a matrix. I'd have something that looked like this. So here, these diagrams are just further explaining the point. If the black dots are the domain and the white dots are the codomain, it's perfectly fine for there to be fewer dots in the codomain, but we must map this element of the domain somewhere. So it has to have an arrow either to this guy or to the other. Whereas in the second chart, it's also perfectly fine for there to be more elements in the codomain, but we have to map each element to only one. So I would need to get rid of this arrow in order to be a function. Okay. Now we'll introduce a little bit of terminology. We have surjections, injections, and bijections. In the examples above, you may have noticed that sometimes there are elements of the codomain which are not in the range. If that does not happen, then we say the function is onto. That is, when everything in the codomain is in the range, we say that the function maps the domain onto the codomain. And the proper word for onto would be surjection. So if we say surjection, that's the same thing as onto, and it simply means that every element in the codomain has a preimage in the domain. So you have this diagram here where you can see this first picture is surjective because you have 3 dots in your codomain and each one is getting mapped by somebody in the domain. Whereas in the second picture, although this is a valid function, it's not a surjective function because this element in the codomain doesn't have any preimage in the domain, so it's not onto. Let's look at an example. We're asked which of the functions are onto. The function f from z to z defined by f of n equals 3n is not onto. We already talked about that the only elements in the range are going to be the multiples of 3. So for example, the number 1 is an integer, but there's no way that I can get 1 by multiplying 3 by an integer. So not surjective or not onto. The next one, G, from the set 1, 2, 3 to the set ABC, and we have this notation here where we can see that 1 is mapped to C, 2 is mapped to A, 3 is mapped to C. This is also not onto because there isn't anything mapped to B. It's a perfectly valid function, but there's nothing mapped to the element B. And then the third example here, H, the function from 1, 2, 3 to 1, 2, 3, where 1 gets mapped to 2, 2 gets mapped to 1, and 3 gets mapped to 3, this is onto, or surjective, because all of the elements here in the codomain are getting mapped from somewhere. So it's important to make this distinction that in order to be a function, a rule cannot assign a single element of the domain to 2 or more different elements of the codomain. However, it is permissible in reverse. A function may assign the same element of the codomain to 2 or more images in the domain. However, if that does not occur, which is to say if each element of the domain is mapped to a different element of the codomain, or each element of the codomain has at most one preimage in the domain, then we say that the function is 1-to-1. We are sending at most one element from the domain to one element of the codomain, hence 1-to-1. And again, the proper term for this is injective. So again, we can see a function which is injective here on the left, because each element in the domain is mapped to a different element in the codomain. And it doesn't matter that this element isn't hit. In this case, we can see that the function is not surjective, but it is injective. Whereas here on the right, you have an image of a map that is not injective, because you have two different elements in the domain that are both going to the same element in the codomain. So this is the reason why it fails to be injective. And we can look at the same examples, or pretty similar examples, to determine which are injective. The first function, f from z to z, defined by f of n as 3n, this is injective. And remember, before we said it was not surjective, but it is injective, because the only way to get a certain image in the codomain, there's only going to be one preimage in the domain. The function g from the set 1, 2, 3 to the set a, b, c, defined by this two-line notation here, where 1 is mapped to c, 2 is mapped to a, and 3 is mapped to a. This is not injective, because of the fact that 2 and 3 are distinct elements in the domain, which are mapped to the same element in the codomain. Finally, the function h from 1, 2, 3 to 1, 2, 3, this is injective, because again, each element in the domain, in the codomain, has a unique predecessor in the domain. So from the examples above, it should be clear that there are functions which are surjective, injective, both, or neither. If a function is both injective and surjective, then we call it bijective. Here we're going to define an inverse image. So when discussing functions, we have a notation, a well-known notation for taking an element of the domain and assigning it to an element in the codomain. So we'll say f of x. We've all seen this notation before. F of x is the image of x in the codomain. It would also be nice to start with some element of the codomain, say some y in the codomain, and talk about which element or elements, if any, from the domain it is the image of. So in words, we would say those x in the domain such that f of x is equal to y. I'm trying to collect all of the x's in the domain that get sent to the same y. So we're going to use the notation f inverse of y, but we want to make sure that we clearly understand that this is not talking about an inverse function. Not all functions have an inverse function, which we know from our algebra class, but for every function, we can define this inverse image. So it's unfortunate that the notation is looking the same, but for our purposes, we want to clearly understand that when we're talking about the inverse image, we're talking about the set of all x in the domain that map to a particular y. So the inverse image is going to be a set. So I want to highlight here, f inverse of an element in the codomain is going to be x belonging to the domain such that f of x maps to y. It is this set. So let's do an example. We'll consider the function f from the set 1, 2, 3, 4, 5, 6 to the set a, b, c, d, given by the two-line notation here. And we want to find the complete inverse image of each element in the codomain. So we have the elements a, b, c, and d in the codomain. If we want to find the pre-images or the inverse images of the element A, then we'll just look at which elements in the domain were sent to A, and it's 1 and 2, so we form the set 1, 2. Similarly, which elements in the domain were sent to B, 3, 4, and 5. And which elements were sent to C. So it looks like I have a typo here, but this should be 3, 4, and 5 were sent to B. And only the element 6 was sent to C. Again, just from reading this table. We can also find the inverse image of the element D, even though no element was mapped to D. We're just looking for the set of all elements that map to D, so that's going to be the empty set. Another example would be if we think about the function g from the set of integers to the set of integers, defined by g of n is equal to n squared plus 1, and we want to find the inverse image of 1, the inverse image of 2, the inverse image of 3, and the inverse image of 10. So to find the inverse image of 1, we need to find all n such that n squared plus 1 equals 1. So I could just solve this equation. If I subtract 1 from both sides, I have n squared equals 0, and clearly 0 is the only number. So it's the singleton set 0. Note that even though there's only one element, we're still going to write it as a set. That's very important, that the inverse image is a set. Similarly, to find the inverse image of 2, we need all integers in n, all integers n, such that n squared plus 1 equals 2. If I subtract 1 from both sides, I get n squared equals 1, and there are two solutions to that equation. N could be negative 1 or positive 1. So this is a set of two elements, negative 1 and positive 1. Then if we do the same thing, we're looking for the inverse image of 3, then subtracting 1 from both sides, I'd have n squared equals 2. And I know that this was a function from the integers to the integers. So this equation doesn't have any solution in the integers. Of course, the square root of 2 is a solution to the equation in the real numbers, but because we are working with discrete functions, the function is from the integers to the integers. So the inverse image is going to be the empty set because there is no integer that solves this equation. Finally, the inverse image of 10 is going to be negative 3 and positive 3 because the function g, sorry, this is g, not f, the function g applied to negative 3 gives you 10, and the function g applied to 3 gives you 10. Since when we're talking about the inverse image, we're always talking about a set, it makes sense to talk about the cardinality of the set, which is going to be the number of elements in the domain which map to the given element. So here's an interesting exercise. Find a function f from the set 1, 2, 3, 4, 5 into the set of natural numbers such that the inverse image of the element 7 is equal, the cardinality is equal to 5. So I'm looking for a function from the set 1, 2, 3, 4, 5 where there are 5 different numbers that all get mapped to 7. Well, there's only one such function because we need 5 different numbers to all get mapped to 7, and there are only 5 elements in our domain to begin with. That means I have to send them all to 7. 1 maps to 7, 2 maps to 7, 3 maps to 7, 4 maps to 7, and 5 maps to 7. So this, I think, would be a very nice question for a test or a quiz to make sure that you understand these concepts here. And then scrolling down, you'll see just a recap of the definitions we've done so far. Function, domain, codomain, and so on. Let's work through a few exercises together. Exercise 1. Write out all possible functions f from the set 1, 2, 3 to the set AB using the two-line notation. then we want to know how many functions are there, how many are injective functions, how many are surjective, and how many are bijective. So as when we were writing elements in the Cartesian product, I think it's going to be helpful to be a little bit orderly here. So I'm going to use the two-line notation, which is the matrix notation. And always across the top, when we're doing this, we just write the elements in the domain. There are 3 elements in the domain, so I'm going to write 1, 2, 3, and then close it off. And I could have a function, a perfectly valid function, that sends all of them to A. Or I could have a function that sends 2 of them to A and 1 of them to B. And it seems like that could happen in 3 different ways, because I can have 1 goes to A, 2 goes to A, and 3 goes to B. Or I could have 1 goes to A, 3 goes to A, and 2 goes to B. Or I could have 2 goes to A, 3 goes to A, and 1 goes to B. Or I could have 2 of them mapping to B and 1 of them mapping to A. So I could have 1 going to A, but 2 goes to B and 3 goes to B. I could have 1 going to B, 2 going to A, and 3 going to B. I could have 1 going to B, 2 going to B, and 3 going to A. And finally, I could have all of them going to B. So all of these are valid functions because for each element in the domain, I've only assigned 1 element in the codomain and exactly 1 element I've assigned. So everybody has an assignment and only 1. So if I count, it looks like there are 8 possibilities. And I need to know how many are injective. So I remind myself that to be injective, it means that each element in the domain gets mapped to a different element in the codomain. Well, none of them are injective. And this comes from the fact that I only had 2 elements in my codomain to start with. I had 3 elements in my domain, so there's no way that I could map 3 elements in my domain to 3 different elements in the codomain, which only has 2 elements. Then the next question is how many are surjective? And it actually looks like most of them are surjective. In order to be surjective, I have to make sure that every element in the codomain has a preimage. So this is surjective, this is surjective, this one, this one, this one, and this one. Only the ones where I mapped them all to A or all to B are not surjective. So I have 6 of them are surjective. The last question is how many are both surjective and injective, which we call bijective. And because I have no injective functions, I can have no bijective functions. So I'm going to write that as well. None of the functions are bijective. Okay, the next example, we're given a table representation of a function f from the set 1, 2, 3, 4, 5 to the set 1, 2, 3, 4. And we're asked, is f injective? F is not injective because looking at my table, I can see that f of 2 is 2 and also f of 5 is 2. But 2 and 5 are distinct elements in the domain. So in order to be injective, they would have to go to distinct elements in the codomain. The next question is f surjective? Well, in fact, it is, because every element in my domain, remember my domain was just the set 1, 2, 3, 4, I have 1, I have 2, I have 3, I have 4. So I'm already surjective. I don't even care about the last one. So since f of 4 is 1, f of 2 is 2, f of 1 is 3, and f of 3 is 4. So every element, 1, 2, 3, and 4, has at least one preimage in the domain. Then we're asked to write the function using the two-line notation. Well, the two-line notation is very similar to this table notation. I'm just going to write the elements of my domain across the top and their corresponding elements in the codomain in the line beneath them. Here's another representation of a function. Now I'm going to notice that my domain is 1, 2, 3, 4, and my codomain is 1, 2, 3, 4. And I just have the graph. So, same question, is f injective? And f is not injective. Because I have two distinct elements in the domain, which are 1 and 4, and they're both going to the same element in the codomain, which is 3. And then I'm asked, is f surjective? In this case, f is not surjective. And that is because there is an element in my codomain, the element 2, that doesn't have any preimage in the domain. So because there is no element in the domain, one, two, three, 4, such that f of x equals 2, it's not surjective. And then we'll write the two-line notation. So again, 1, 2, 3, 4, I write the elements in my domain across the top, and I just have to see where they're mapped. 1 maps to 3, 2 maps to 4, so 1 maps to 3, 2 maps to 4, and 3 maps to 1, 4 maps to 3. So this is my two-line notation for the function. Now, let A be the set 1, 2, 3, up to 10. We're going to consider a function f from the power set of A to the natural numbers given by f of capital B equal to cardinality of B. So because they told us that the function f was from the power set to the natural numbers, and we know that the elements in the power set are sets, we're going to interpret that B is a set. So I apply the function to a set B, and the rule of the function is that it's giving me back the cardinality of the set B. The question is, will this function be injective? This function is not injective because there are many elements in the power set that have the same cardinality. For example, I know that singleton 1 belongs to the power set of A, and singleton 2 belongs to the power set of A, and f of singleton 1 is equal to the cardinality of singleton 1, which is 1, which is also the cardinality of singleton 2, which is f of singleton 2. But these two sets were not equal. Singleton 1 is not the same set as singleton 2, so I get to say f is not injective. Is it surjective? Well, remember, the codomain is the natural numbers. So in order to be surjective, I would have to have a set in the power set with cardinality for every natural number. So it's not surjective. It's not surjective because every set in the power set of A has cardinality less than or equal to 10. So all of the natural numbers larger than 10 don't have any pre-image in the domain. Then we're asked to find F inverse of 1. I'm sorry, the pre-image, the inverse image of 1. So the inverse image of 1 is going to be the set of all elements in the power set which map to 1, or the set of all elements in the power set that have cardinality 1. So we know these are the singletons. We know that the elements in our power set are sets, so the elements in the inverse image will also be sets. We're looking for all of the sets in the power set of cardinality 1, so it's just all of the singletons 1, 2, 3, up to 10. Then we're looking for the inverse image of 0. So we're looking for a set in the power set that has cardinality 0. And the only set in the power set that has cardinality 0 is the empty set. And remember, this inverse image is a set, so it's going to be a set that contains the empty set. Whereas it also asks us to find the inverse image of 12. And we already said in part B that every set in the power set of A has cardinality less than or equal to 10. So there is no set in the power set of A that has cardinality 12, which means the inverse image of 12 is the empty set. So I want to make this distinction here between these two answers. The inverse image of 0 gave us the set containing the empty set, whereas the inverse image of 12 is the empty set itself. These are not the same. The next exercise says let A be the set of elements in the natural numbers from 0 to 999 inclusive. So that is all of the numbers with 3 or fewer digits, and we're going to define a function from this set A into the natural numbers by f of a 3-digit number is going to be the sum of the digits. And it gives you the example here. If the number we chose was 253, then 2 plus 5 plus 3 would be 10. And I want to point out here that it said that our domain A is going to include numbers with 3 or fewer digits, so it's going to include numbers like 25, 19, and 7 that don't have 3 digits. So what we're going to do is we're just going to consider the missing digits as zeros. So if I was applying the function to the number 7, I would add 0 plus 0 plus 7. If I was applying it to 19, I'd add 0 plus 1 plus 9. Okay, so we want to find the inverse image of 3. That means I want to find the set of all natural numbers of 3 digits or fewer, the sum of the digits being 3. So the inverse image of 3, well, I could have 3 because I would think of it as 0, 0, 3. Or I could have 30, 0, 3, 0. Or I could have 300. Also, I could have 12, if I think of it as 0, 1, and 2. or I could have 21, or I could have 102, and then I could have 120, I could have 201, 210, and I think that's all I could do with 0, 1, and 2, but I could have 1, 1, and 1. That's a perfectly valid 3-digit number. So I found 10 answers. I believe I've got all of them. And the way that I did this was sort of thinking of, well, how many ways can I add up to 3? It can either be 3, or it can be 1 plus 2, or it can be 1 plus 1 plus 1, and then just permuting these digits. The next question is to find the inverse image of 28. Now, one thing to notice is that the largest number in our domain is 999. And when I add the digits, I get 27. So 27 is actually the largest number in the range of the function. We could try, if we wanted to find a number whose digits add up to 28, but the largest number I could pick for the first digit is 9, the largest number for the second digit is 9, and the largest number for the third digit is 9. So clearly we can't get any higher than 27. So this is actually going to be the empty set. Is the function injective? In part A, we found an image in the codomain that has 10 preimages in the domain, so clearly not injective, since 3 and 30 and 300 and all of these other numbers are distinct domain elements that all map to the same element in the codomain. And then it asks, is F surjective? Well, again, I'll refer you to the above. In part B, we found an element in the codomain that has no predecessor in the domain. So using part B, I can see that F is not surjective. Next question, 9. Find a set X and a function F from the set X into the natural numbers, so that the preimage of 0 union with the inverse image of 1 is giving you X. So I'm going to do that up here. So probably the cheapest thing we could do is say, well, I'm just asked to find any set X, so let me take X to be the set, any 2-element set. Well, for that matter, I could take a 1-element set. But just to keep things simple, let's do a 2-element set, and let's say that my rule of the function is going to be f of A is 0 and f of B is 1. That's my rule. So when I take the preimage of 0, I find that that's the set singleton A. And when I take the preimage of 1, I find that that's the set singleton B. And singleton A union singleton B is X. That's exactly what I wanted. So that's a perfectly good example. Maybe a more fun and interesting example would be, let's take X to be the set of real numbers, and let F from the set of real numbers to the set of natural numbers. Be defined via f of any real number x is 0 if x is a rational number, or 1 if x is not a rational number, if it's irrational. So that's 0 if x is rational, 1 if it's not. And we know from our previous lectures that the rational numbers and the irrational numbers together make up the real numbers. So then we have the pre-image of 0 is the rational numbers. The pre-image of 1 is the irrational numbers, which is the complement of the rational numbers in R. And the rational numbers together with the irrational numbers gives you R. So you can have fun coming up with these examples. Next, suppose that f from x to y is a function. Which of the following are possible? And then explain. So, is it possible that f is injective but not surjective? Definitely. We have already seen examples of this, but a simple one might be, let's take our domain to be the set 1, 2, 3, and our codomain to be the set of natural numbers. Then if we do just map 1 to 1, 2 to 2, 3 to 3, clearly I'm not surjective because there are a lot of natural numbers that I didn't use. What about surjective but not injective? We've also seen examples of this. So let's take the domain to be 1, 2, 3 and the codomain to be singleton 19. And I'm going to define my function 1 goes to 19, 2 goes to 19, and 3 goes to 19. Well, clearly I'm surjective because every element in the codomain has a preimage in the domain, but I'm not injective because I've got different elements in the domain mapping to the same element in the codomain. What about if the cardinality of x and y are equal? Then can f be injective but not surjective? Well, we also had an example of this. We took a function from the natural numbers to the natural numbers. Certainly their cardinalities are equal because they're the same set, but we sent f of n to 3 times n. So the range is only the multiples of 3, not the full codomain, so it's not surjective. What about the cardinalities of x and y are equal? F is surjective but not injective. We could also have that if I took a function from the integers to the natural numbers and I defined it by f of n is equal to absolute value of n, for example. The cardinalities of the integers and the natural numbers are equal. They're both infinity. And we discussed when we talked about cardinality that we have different ideas about infinity, but for our purposes, we're just talking about these discrete sets. We're just going to take it so far as to say they're both of infinite cardinality. But clearly it's not injective because the absolute value function, both -1 and +1, will give you back 1, and so on. Then it says, well, what if the cardinality of x is equal to the cardinality of y, and x and y are finite in cardinality? Then can f be injective but not surjective? And here's where we would say this is not possible. Why not? Well, if f is injective, then as we know, each element in the domain has a different element in the codomain. So the range of f will have the same cardinality as the domain. But the domain has the same cardinality as the codomain by assumption. So the range and the codomain are equal. So it's surjective. Also, if x and y are of finite cardinality, cardinality of x is equal to cardinality of y, and f is surjective but not injective, it's also not possible for f to be surjective but not injective, is what I'm trying to say. Since if f is surjective, then the domain, the cardinality of the range will now be equal to the cardinality of the codomain, because it's surjective by assumption. And then that will be equal to the cardinality of the range. To the domain. So for the cardinality of the range and the cardinality of the domain to be equal, will be injective. So it's possible to have two sets of the same cardinality and a function be injective but not surjective, or vice versa, only if they have infinite cardinalities. Very interesting. Okay. Lastly, we want to think a little bit about function composition. So if f is a function from a set x to a set y, g is a function from a set y to a set z, we'll define the composition of f and g just like we did in an algebra class, using this notation g open circle f from the set x to the set z. The image of each x in the set x under this composition is going to be g of f of x. That is, we're going to plug x first into f and find its image in y. Then we'll plug that image into g and find its resulting image in z, just like in algebra. Okay, and the questions are, A, if f and g are both injective, must g composed f be injective? Yes. So what does it mean that f and g are both injective? Let's think about the composition. We want to know if two elements are equal under the composition. So g composed f of some element A is equal to g composed f of some element B. And remember, these elements are coming from the set X. Does that mean that A and B have to be equal? If so, we're going to say it's injective. Well, this is g of f of A, and this is g of f of B. And we know that f is injective. And we know that g is injective. So since g is injective, we can say f of A must equal f of B. And since f is injective, it must be that A equals B. Because if A weren't equal to B, then f of A couldn't be equal to f of B. If f of A wasn't equal to f of B, then when I applied g on them, they wouldn't go to the same place. So we conclude that the composition is injective. Now what about with surjection? If f and g are both surjective, is the composition definitely surjective? Well, yes, again. So for all little z in my codomain z, because g is injective, we can find a y in the domain of g that maps to little z. That's the definition of g being surjective. And for all little y in the domain, in the codomain of f, there exists a little x in the domain of x, in the domain of f, that maps to little y. That's the definition of f being surjective. So if we take this little x and we apply the composition to it this is g of f of x, which is g of y, which I already know is little z. So for any little z in my codomain, I can find, using the surjectivity of g and f, its preimage in the domain. Hence the composition is surjective. Now, if the composition is injective, is there anything we can say about f and g? Well, there is. Since the composition is injective, g composed f of x equal to g composed f of y only happens if x is equal to y. So then if I have f of x equal to f of y, then clearly g composed f of x is going to be equal to g composed f of y, so x equals y. That means that f will be an injective function. So I can at least say that much. It asks us, what, if anything, can you say? Well, the best I can do is I can say definitely f is injective. Not sure about g or about the surjectivity, but definitely f is injective. And similarly, it asks us if the composition is surjective, can we say anything about f and g? We can. So let's take a little z in z. Since the composition is surjective, there exists a little x in the domain x such that the composition takes little x to z. So every little z in the codomain capital Z has some preimage in the domain x. And g composed f of x equals z is the same thing as g of f of x equals z. So let's let y equal this little f of x. Then for all z in capital Z, we have a y in y such that g of y equals little z. So what did we determine? We determined that g is surjective. So again, the question just asked us, is there anything we can say about this composition? And we can say, for sure g is surjective. I don't know about f. I didn't say anything about injectivity, but the composition being surjective means that this function g is surjective, or the composition being injective means that this function f is injective. And it does matter which order we're composing them in. Note that if we had f compose g, it would be different. Then we would say if the composition is injective, then g is injective. And if we had f compose g surjective, then we would say that f was surjective. So just pay attention to the order here. But this is what we can conclude. And that is the last exercise.